Talking of dates, data, one of the challenges we have that I have already discussed in the previous sessions of this workshop in the previous years is the fact that because at the moment most of the state of the art in machine learning and deep learning in particular is with fully supervised training, we face two challenges. The first one is that we need to collect, of course, but it's true overall, we need to collect as much as possible quality data in order to cover all these operational domains that I mentioned, all the conditions, etc., which is obviously complex and costly and time demanding, but also sometimes not, well, very dangerous if you want to have very specific and dangerous situations. And on top of that, because of this full supervised paradigm that we use, sorry for the typo here. So you need to do labeling, usually manually, and this is really a nightmare. Just using examples here from three data sets, which are Cityscapes, PEDEX, and JAD. The first one, you see that annotating very, with all the details, all the scene elements, in particular the pedestrians, the cyclists, and their bicycles, etc., is obviously very time demanding. So this is the typical 2D semantic segmentation setup. Now looking at the pedestrians, if you on top of that you want to have 2D pose annotated, and even more so the 3D volume and pose annotated, etc., it's very difficult if possible at all. And in this data set, actually part of this very sophisticated annotation is done automatically. And last example, which is about detailed attributes from JAD. Again, it's clearly feasible by hand this time, but it's very time demanding, and sometimes it's very ambiguous. It's not very easy to perform. And at the end of the day, no matter how much time and energy you throw in this annotation and data collection, it's quite likely to be insufficient for the level of security that we wish to reach. So what can we do about that? Well, first of all, we must keep pushing with the quality data sets, and luckily enough, the whole community, whether academia or industry, industrial labs, they keep pushing, and there is a large offer of publicly available data sets, driving data sets, which are fairly generalist. So this is a list which is not completely exhaustive, but give a sense of what has happened in the last 15 days or so, 15 years or so, sorry. And you see just in the last 2 years or 1.5 years, there were really many new data sets which are really interesting. And most of them, they are multi-sensor with cameras always or almost always, but also LiDAR. And you have 2D, 3D annotations of objects in terms of boxes and semantic segmentation. So including the VRUs. So it's very interesting to use these data sets. But besides that, and as I was saying in the introduction, we need things which are also really dedicated to the vulnerable road users. As it turns out, there are quite a few. Before I move to them, I just like to make just to highlight some things that we have released, which are also generalists, but I think they are interesting and maybe singular on their own way. The first one, which is called Woodscape, and you see an example here where with at least on the top, you see 3D bounding boxes plus semantic segmentation of motorbike and the rider. So this data set is about, in particular, fish-eye wide-angle cameras, which are very common in the automotive. So you can check out the data set on the website. And the other one, which is way smaller, but even more singular, it's about radar. So we have released this data set with automotive radar, in which we have annotated cars, pedestrians, and cyclists. And you see an excerpt here with what is called two different views of the radar tensor. The first one is angle and range, and the other one is angle and Doppler. And it tells you not only the distance, the position of an object, but also the relative speed. And the box that you see at the bottom is the pedestrian that you see in the two views. And again, you please go and check the website of the dataset if you find that interesting. But what I was saying is that we also need specialized data sets for VRUs. So in the last 10 years or a bit more than 10 years, there were quite a few, but it's probably half of what we have for driving scenes in general. But it's already a wealth, and you see some of the most popular here, including PEDEX that I have already mentioned. And most of them they are about pedestrians. Some of them have on top of that also other people like riders. They all have, I believe, 2D bounding boxes for these road users, and sometimes there are more things like attributes, action, intention, trajectory, etc. But as I was saying earlier, these data sets are necessary, but probably not enough. So we have to think in terms of alternative supervision to go further and improve the safety. So there are many tools for machine learning to do alternative supervision. I'm not going to go through it, and I will just illustrate in the rest of my presentation a few things that we've been doing in the team, but they are essentially representative of trends in the field. I will show examples of the use of domain adaptation in relation with VRUs, and then I will move on to do detailed analysis in the form of multitask learning with different attributes, and I will then show how to use synthetic pedestrians in real images to improve performance in certain cases. And if time permits, I will just show a very quick sneak preview of a recent work about physics awareness for monocular motion capture. So domain adaptation, it is the problem of learning on data of a certain domain, which is annotated, but at test time you have different conditions. And for this test time, which is called target domain, you have data but not annotated. So we 2 years ago at CVPR we had this work which was actually more focused on semantic segmentation, but I'm showing here one result about object detection. Let me start with the result, and then I will say a few words about how it works. So in these images, which are from Cityscapes Foggy, where the images are real and actually the fog is artificial, one can see some artifacts, but it's depth-based. These are the 3 images on which, if you just run pedestrian detector train on cityscapes without fog, this is what you get. Not only pedestrian, actually, also other objects as well, but just look at the pedestrians in orange. Even on the third scene, you don't detect anything. And using the the entropy-based adversarial method that we proposed 2 years ago, you can recover all these detections, in particular, way more pedestrians and bicycles, etc. And in the little table, you see the numbers. So quite a dramatic improvement in performance, although the performance is still not that good, but at least it helps reducing the domain gap. And a few words about how it works. So as a number of very successful unsupervised domain adaptation methods that we've seen in the past years, it relies on adversarial training, which allows the system to align the distributions close to the output of the network. In our case, we look actually at the predictive entropy that we want to align with between target and source domains, and also to minimize in order to reduce the confusion of the model on target domain images. And also another ingredient which we found very useful and for domain adaptation is self-training, which means that you can use the first version of the model, for instance, the one which has been trained only on the source domain data under full supervision, and you can use that to annotate your training an example from the target domain. And then you can use these pseudo labels to improve your model. So on this little diagram, you see at train time, first of all, you have source domain examples, which are labeled. So you can use them to train under full supervision your model. In the previous case, it was an object detector. But you also, what we consider is that we look at the the logits and the entropy of the distribution at the output of the model, and we consider unlabeled target domain examples, and we align using a discriminator. So through an adversarial training, we align these close to output activations between source and target. So the discriminator is, by trying to discriminate these source and target examples, force the model to really align things close to the output. And at runtime, of course, you just have new target domain examples that you have to analyze. So moving on to the second work I wanted to highlight, which is called Artificial Dummies, with Antonin Wobecki and colleagues at CTU in Prague. So this work is about creating and including fake pedestrians in real scenes. So in all these images, you can try and spot. Sometimes it's easier because there is only one person in the scene. And the idea is really to augment data with the control on the appearance and the pose of the pedestrians. So in a nutshell, and also why we call it dummies, it's in reference of these little mannequins you see on the right, these little dolls, not so little actually, mind-sized dolls that are used to on test tracks in the automotive industry. So now we are having these synthetic humans that we include in visual scenes. So they are created with a conditional GAN, as I said, with the control of the appearance and the pose, and also the blending of the synthetic person in the scene. And we use that to augment real data sets, in particular at night, but not only. And it does improve, and then we train, say, a detector on these augmented data, and it improves the performance, sometimes significantly, in particular in low data regimes. We developed this project mostly for improving the performance of the train model, but the same principle can serve as well for the validation of an existing model, which is a key issue in the safety critical systems. We need really to test and validate them, and in particular in terms of certifying the behavior on corner cases. So we believe this work can help toward that. The way it works, this is a simplified representation of the pipeline. So we train a data generator, which takes several inputs. Somebody has a microphone open, I think. And the system takes as input an example real person, from which we are going to sort of steal the appearance with an encoder. A candidate pose in the form of 2D joints, which are generated from an actual learned distributions of poses from real images. And then we have also the background, which is actually the image patch in the scene in which we want to incorporate the character. And we feed that at different levels of the conditional GAN in order to get, as you see in this example, in the red. I don't know if you see my arrow, my pointer, but you see here now we have provided this image patch, this pose, this appearance, and we get this new guy with the specified pose and somehow the right appearance. And you see other examples here, and you see the example now in context, and this example as well in context. And then we do that at scale, and we can then retrain our system. And what you see, I'm going to exemplify that a bit later, but that we in particular recover a large number of misdetections with, in the case of low data regimes. Just two other examples before showing the numbers. So in these two scenes, these two pedestrians, these two persons are actually fake. It's a bit slightly more visible on the night scene. And if I just zoom in, this is what we get. Interestingly enough, I think on the right, the guy has naked foot, which is not quite right. But anyhow, and this is another interesting question, despite the artifacts and it doesn't hinder necessarily, on the contrary, actually the performance of the the model that you train on this extended data. Talking of which, these are examples and numbers. So what you see on the left is in blue is the original detection of CSP, I think, a state-of-the-art object detector, but trained with little data. And this is, and there are a number of false negative. And if now we retrain it with the augmented data with the method I just presented, we recover all the additional detections in green, which are correct ones, and they correspond to occluded or low-res pedestrians. So it's quite satisfactory. Another example that you see in numbers on the right is a nighttime scenario. So in this case, the setup is the following. We use cityscapes to train a pedestrian detector, which in this case is a faster RCNN. And we want to use it at night. So we use data from the night owls data set, but only with images without pedestrians. And actually, so it's just backgrounds if you wish, just to emulate the scenario where we have two rare examples in the target domain conditions. And we compare different ways to augment these data. So the nighttime data with artificial persons, so different methods, AdGAN, Surreal, CPL, H 3.6 million, and the one we propose. And you see the performance on three types of detections, three types of three levels of difficulties. One is the reasonable setup, the other one small, and the third one partial. And you see that in the three cases, the lower the better. The figure, it's the metric is the log average. The log average miss rate, which is quite classic in object detection, and you see that we get the best result in this example. So. Of course, it's an emulation of in terms of scenario. We do have real pedestrians in night owls because it's actually the goal of this data set. But we just wanted to make the point that in this case, the detector has never seen real humans at night. Third projects that I wanted to highlight is now looking at closer at pedestrian, not only their position, but also maybe their pose or other attributes. So let me start with this little video, which was actually from a demo that Valeo did at CES in 2020, at the time where it was still a real event, not virtual one. And what you see is built on top of the PIF-PAF human pose detector from EPFL, and we use that then to learn attribute classifier in terms of in particular the attention of the pedestrian and the action he or she is going to undertake. A follow-up work on this project is this more recent one, which we actually did with the team of Alexandre Alahi at EPFL, and that's the work of Taylor Mordan. So here you see just the detection, and now this is a test example, and I zoom in and show what are the attributes which have been recognized. Actually, maybe some of the answers are not correct, but you can also appreciate the difficulty in some cases. I'm not sure that I could tell myself what is the true answer. But so these are some of the attributes out of 32 attributes, including the gender, the age, the clothing, the appearance, the action, whether the person is using a mobile phone, etc. All very interesting. As you can imagine, very interesting things to understand. So you have so many things to predict, and with limited budget, so it makes sense to use it with a multi-task learning framework. So this is another example, just to show you a bit of diversity. So the work is relying heavily on multitask learning. So effectively, we have a single shared encoder, and we have 32 heads, which are very shallow actually. And this allows to, of course, reduce the computational cost, especially for something which needs to run in a car, but also to share the knowledge between the annotations and the data sets. In this case, we use only one data set, but you could use multiple data sets with multiple types of annotations. The architecture itself is based on the PIF-PAF work of Kreis in 19 from this EPFL team. It's based on what is called composite fields, and it's a framework where the system regresses essentially scalar or vectorial fields, and that can be used both for detection and analysis altogether. As for training, we used this very interesting data sets called JAD for joint attention and autonomous driving, where you have all these attributes annotated, so they went through the pain of having these very detailed annotations. And one thing that one challenge that we faced is how to deal with all training time with so many tasks at the same time. So how to deal with the balance between the gradients flowing back from the different heads, in particular in the shared encoder. So we found a way to do that, but before I can show you the architecture. Maybe just for the sake of time, just move to these two panels here. What you see here is the one of the fields which is output by the system, and this one is for the localization. So it's per cell you have some. It's a scalar field essentially, which tells for each cell in the image whether it belongs to a pedestrian or not. And you can also have a vectoral field here. Each vector tells you for a cell where is the center of the most likely pedestrian it belongs to, if any. And you have other fields for other attributes. Then they can be they are discrete in this case. Just numbers, if I have time, maybe not. So there is a journal paper under revision on that, so you can check out. But just to say that regarding the balancing of the gradient, so what we did is that this is what is indicated at the bottom, at the top right part of the slide, is that we have this classic compound laws for all the tasks. Capital T is the number of tasks, and the gradient. So the problem is not in the individual heads, but for the shared backbone. And for this one, we weigh, which is a classic thing to do. We weigh each gradient for each head. But in our case, the way kappa T is in the form is the it depends only on the number of tasks. The point here is to make sure to have a generic method, no matter how many tasks you have. And we found this scaling that work well, and it's something that we explain in the paper with a lot of comparisons, both in terms of classification and of the attributes, and also detection of the attributes. So I'm not going to go through the details, and for the last 30 seconds or so I will just show images, no equations of this very recent work, just sneak preview. It's not specifically about pedestrians, but it's a work which might be useful one day for driving scene understanding. Work with the team of Christian Theobald at MPI in Saarbrücken, with Shimada in particular. It will be presented at SIGGRAPH in August, and it's about monocular motion capture. And the interesting part of this work is how it's a machine learning approach where there is a lot of physics involved in particular in the form of dynamics, including the actual modeling of the ground reaction forces, and also all the classic dynamical equations for articulated body, etc. And some of the ingredients being learned through examples. So the system takes 2D key points as input and provide the 3D pose through time. So just let me show. Oops. Let me just remove the sun, and you see, yes, we are not quite in the streets here, but you understand that being able to do this type of 3D pose estimation with no foot penetration, physical correctness, etc., can be very important, especially for pedestrians which are very close to the ego car. And with this, I'm going to stop with conclusion and takeaways. Very important to look at the VRUs in particular. Probably we still need, as a community, to push towards more data, more annotation, and also leveraging other forms of supervisions. Getting good performances on the training set is not enough. You have to make sure it's good on other conditions, other domains, so which brings the issue of validation and certification. And on a side note is that what I'm seeing here about the VRUs, and particularly the pedestrians around the car, we have also problems at similar interesting challenges at analyzing the people inside the ego car. So it's called interior and driver monitorings. And I really think we should look at that as a community. And for this one, we really definitely like data. And this is the end of my presentation, with the thanks to all my team and the places where you can find all the information about our work, data sets, and latest news. Thank you very much.
Thank you, Patrick. So I should have